In this module, we shall study about Sharpe's single index model continued. William Sharpe tried to simplify the data input and data tabulation required for the Markowitz model. He attempted to achieve a satisfactory simplification by abandoning the covariance of each security by substituting it with the relationship of each security with market index. This is known as the Sharpe's single index model. After studying this module, you shall be able to understand the Sharpe's single index model, understand the market model, explain the basic assumptions underlying Sharpe's single index model, measure the risk and return of portfolio under Sharpe model. We shall now discuss the simple Sharpe's optimization solution. The single index model SIM developed by William Sharpe is a simple asset pricing model that measures both risk and return of a stock. It is simplification of the Markowitz portfolio optimization theory. The single index model observes that the return on most assets, each security, moves in relation to the return on overall market index as measured by the market portfolio or market index. Market portfolio is the aggregate of all risky stocks in the market, where each stock has a proportion in the market portfolio equal to the market value of the stock divided by the sum of market value of all stocks in the market. The market value of each stock is equal to price per share times the number of shares outstanding. Such a portfolio represents whole of the market and moves in alignment with the market. The beta of the market portfolio is always equal to 1. A general or representative index of the market such as BSE Sensex or Nifty could be used in the absence of the market index. Single index model captures the relative contribution of each stock towards portfolio risk. The portfolio risk declines through diversification, but to an extent. The part of the risk that cannot be further reduced is attributed to the market forces influences operating in a given market and is called the systematic or undiversifiable risk measured through beta. The contribution of each individual stock to the portfolio risk can be identified by relating its return with the market portfolio. William Sharpe expressed this relationship with the simple regression equation. He identified this relationship by regressing the return on security I dependent variable on the corresponding return on the market index independent variable. The single index model for return on security I is expressed as Ri is equal to alpha I plus beta I into Rm plus Ei. Equation 1, where Ri is equal to the random uncertain total return on security I, alpha I is equal to alpha, the non-random component of security I's return that is unique, firm specific to asset I, beta I is equal to beta, a measure of sensitivity of security I's return to the return on market portfolio, Rm is equal to the random uncertain total return on market portfolio, Ei is equal to epsilon, the random component of security I, return that is unique, firm specific to security I. Epsilon is sometimes referred to as random error disturbance or error term. Note that alpha I and beta I are constants. The SIM decomposes the total return on security I into a unique component and alpha I plus epsilon I and a market component beta I into Rm. The unique component is further divided into non-random certain unique component alpha I and a random uncertain unique component Ei. The model also identifies the two sources of risk in the security's total return. First, market or systematic risk attributable to market related factors which are reflected in beta I, RM, and second, firm specific or non-systematic source reflected in EI. Let us now understand the assumptions of Sharpe's single index model. The single index model lies on three basic assumptions. If only first two assumptions of the following three are made, the model is referred to as the market model instead of Sharpe's single index model. The assumptions are as follows. Assumption 1. The error term EI has an expected value of 0 and finite variance. Our first assumption and construction, if necessary, gives the SIM expression for the securities I's total return as R dot I bar is equal to alpha I plus beta I into Rm dot bar. Equation 2. The above SIM expression holds for all assets, both individual assets and portfolio of securities. Therefore, SIM expression for expected return of market portfolio is Rm dot bar is equal to alpha m plus beta m into Rm dot bar. Equation 3. The above equality could be held true for any possible value of Rm when alpha m is equal to 0 and beta m is equal to 1. In other words, the market portfolio has an alpha equal to 0 and beta equal to 1. Similarly, the SIM expression for the expected return of a portfolio may be taken as portfolio alpha plus portfolio beta times expected market return. Thus, Rp dot bar is equal to alpha p plus beta p into Rm dot bar. Equation 4. The portfolio alpha is the weighted average of the specific returns alphas of the individual securities. Thus, alpha p is equal to summation of I is equal to 1 till n Wi into alpha I. Equation 5, where Wi is equal to proportion of investment in an individual security. Alpha I is equal to specific return of an individual security. Here, portfolio beta is the weighted average of the beta coefficients of individual securities. Thus, beta p is equal to summation I is equal to 1 till n Wi into beta I. Equation 6, where Wi is equal to proportion of investment in an individual security. Beta I is equal to beta coefficient of an individual security. Therefore, the expected return of a portfolio is the sum of the weighted average of the specific returns and the weighted average of the market related returns of individual securities. Assumption 2. Now, we introduce the second assumption. The covariance between the return on market portfolio and the securities random error term is 0. Mathematically, covariance of EI and Rm is equal to 0. Equation 7. The assumption interprets that the error term epsilon is the firm specific component of the securities I's return. This assumption also leads to two mathematical expressions: the securities total risk sigma I square and the securities market risk beta I. Securities total risk. We know that securities variance of return is sigma I square is equal to E in bracket Ri minus Ri dot bar whole square. Equation 8. Substituting SIM formula for Ri and Ri dot bar, we have sigma I square is equal to E in bracket alpha I plus beta I into Rm plus EI bracket close minus alpha I plus beta I Rm dot bar whole square is equal to E in bracket beta I bracket open Rm minus Rm dot bar plus EI whole square bracket close. E in bracket beta I square into Rm minus Rm dot bar whole square plus 2 beta I into Rm minus Rm dot bar multiplied by EI plus E in bracket EI whole square, which is equal to beta I square into sigma m square plus 2 beta I into sigma m into EI plus sigma EI square. Note that since EI is equal to 0 and sigma EI square is equal to capital E into EI minus EI bar whole square, which is equal to capital E into EI whole square. Given the second assumption that sigma EIM is equal to 0, we have the following SIM expression for security I's total variance or total risk. Sigma I square is equal to beta I square into sigma m square plus sigma EI square. Equation 9. The single index model decomposes the asset's total risk into market related component or the explained risk beta I square into sigma m square and a unique firm specific component of risk or unexplained risk sigma EI square. Securities market risk. Now we look at the expression for sigma EIM. Sigma m EI is equal to capital E Rm minus Rm dot into EI minus EI bar. Capital E into Rm minus Rm dot bar into EI minus EI bar is equal to capital E into Rm minus Rm dot bar into Ri minus alpha I minus beta I into Rm minus Ri dot bar minus alpha I minus beta I Rm dot bar, which is equal to capital E Rm minus Rm dot bar into Ri minus Ri dot bar minus beta I into Rm minus Rm dot bar, which is equal to capital E into Rm minus Rm dot bar into Ri minus Ri dot bar minus beta I into Rm minus Rn dot bar whole square, which is equal to capital E Rm minus Rn dot bar into Ri minus Ri dot bar minus beta I into sigma m square, which is equal to sigma Im minus beta I into sigma m square. If sigma MEI is assumed to be equal to 0, then 0 is equal to sigma Im minus beta I sigma m square. This implies beta I is equal to sigma Im upon sigma m square. Equation 10. So, given our second assumption, an asset's market risk is equal to assets covariance with the market portfolio divided by variance of market portfolio. This is true for all assets, both individual securities and portfolio of securities. Therefore, SIM expression for a portfolio's total risk is sigma p square is equal to beta p square into sigma m square plus sigma ep square. Equation 11, where sigma ep square is equal to summation I is equal to 1 till n wi square into sigma ei square. Equation 12. Next, assumption third. We now come to the last and the most important assumption of SIM that differentiates it from many other single index model such as the market model. The assumption says that the covariance between the error terms for security I and error term for any other security is 0. Mathematically, sigma ei ej is equal to 0. Equation 13. This implies that the systematic co-movement between the total return of any two securities is because of their sensitivity to the market portfolio and not on any additional forces. Until now, we have SIM expressions for total expected return and total risk variance. We now need to find the SIM expression for covariance between the total return of security I and security j, sigma ij. Note that sigma ei ej is equal to capital E ei ej, which is equal to sigma ij is equal to capital E into Ri minus Ri dot bar into Rj minus Rj dot bar, which is equal to capital E into alpha I plus beta I into Rm plus Ei minus alpha I plus beta I into Rm dot bar into alpha I plus beta j into Rm plus Ej minus alpha j plus beta j Rm dot bar, which is equal to capital E beta I into Rm minus Rm dot bar plus Ei into beta j into Rm minus Rm dot bar plus Ej, which is equal to capital E beta I beta j into Rm minus Rm dot bar whole square plus beta I into Rm minus Rm dot bar into Ej plus beta j into Rm minus Rm dot bar Ei plus Ei into Ej, which is equal to beta I into beta j into capital E into Rm minus Rm dot bar whole square plus beta I into capital E into Rm minus Rm dot bar into Ej plus beta I into capital E Rm minus Rm dot bar into Ei plus capital E into Ei into Ej, which is equal to beta I into beta j sigma m square plus beta I into sigma m Ej plus beta j into sigma m Ei plus sigma Ei Ej, which is equal to beta I beta j sigma m square. Therefore, sigma Ij is equal to beta I into beta j into sigma m square. Equation 14th. To summarize, given the single index model equation, Ri is equal to alpha I plus beta I into Rm plus Ei, and the three assumptions as A. Finite means and variances E is equal to 0, B. Sigma m Ei is equal to 0, and C. Sigma Ei Ej is equal to 0. We obtain the following expressions for the estimates or inputs required for the Markowitz portfolio optimization solution. A. Ri dot bar is equal to alpha I plus beta I into Rm dot bar. B. Sigma I square is equal to beta I square into sigma m square plus sigma Ei square. C. Sigma Ij is equal to beta I into beta j sigma m square, where beta I is equal to sigma Im upon sigma m square and alpha I is equal to Ri dot bar minus beta I into Rm dot bar. Using the Sharpe single index model, we now need n estimates of beta, 1 estimate of the market portfolio variance, n estimates of each asset's total variance or n estimates of each asset's unique variance, and n estimates of expected return or n estimates of alpha plus 1 estimate of market's expected return for a total of 3n plus 1 into 3n plus 2 estimates. Let us now recapitulate what we have learned so far. Markowitz model is highly information intensive. If there are n securities in a portfolio, it requires n expected returns, n variance terms and n into n minus 1 upon 2 covariance terms. William Sharpe developed the single index model which expresses the return on each security as a function of the return in a broad market index as follows. Ri is equal to alpha I plus beta I into Rm plus Ei. Formula for calculation of return of portfolio is Rp dot bar is equal to summation where value I is equal to 1 till n Wi into alpha I plus beta I into Rm dot bar. Risk of a portfolio is measured by sigma p whole square is equal to beta p square plus summation value I is equal to 1 till n Wi square into sigma Ei square. The single index model is built upon following assumptions. First, the error term has an expected value of 0, that is E is equal to 0 and a finite variance. Second, there is no correlation between the error term and the return on market portfolio, that is sigma Em is equal to 0. Third, there is no correlation between error term for security I and error term for any other security, that is sigma ei ej is equal to 0. Based on the above assumptions, following equations are used as inputs required for applying Markowitz model. A. Ri dot bar is equal to alpha I plus beta I into Rm dot bar. B. Sigma I square is equal to beta I square into sigma m square plus sigma ei square. C. Sigma ij is equal to beta I into beta j into sigma m square. Single index model is a simplification of the Markowitz model. If there are n securities in a portfolio, we now require 3n plus 2 estimates instead of n into n plus 3 upon 2 estimates as in the case of Markowitz model.